Welcome back, welcome back, welcome back. I'm Lisa Blackburn. This is my YouTube channel for everything I want to talk about science and math. Today we're in AP Chemistry, Unit 3 by the College Board, and we are finishing up the notes with 3.10. Now there is a previous video that this is going to overlap just a little bit. So if you were watching the other one, you'll notice it cut off in the middle of 3.10. Well, we're starting back at the beginning of 3.10. All right. More about solubility. So y'all already know this. In general, like dissolves like. See, so easy. That is really thin. Let's see if I can make it fatter. Draw thickness. Oop, let's make it a little thicker. Yeah, that's a little better. Okay, like dissolves like. Now, on the AP test, you can't write like dissolves like as a reason. You have to explain why like dissolves like. Like you could say that it's a nonpolar solute, so it's going to have a nonpolar solvent or something like that. This is not considered good enough for a reason, but it's a good thing to help you remember lots of stuff. So in general, polar dissolves polar. I think that still could be a little fatter. And nonpolar dissolves nonpolar. Yeah, that's better. Okay, so a precipitant is one phase forming in another phase. Because we hear it on the weather all the time that there's going to be precipitation, and that means snow or rain in gas. But in chemistry, we're usually dealing with liquids, so we're talking about a solid forming a liquid. Oh, that's a better thickness, isn't it? For example problem, which would dissolve in water? Was that too fast? Did y'all get that? Y'all should know those blanks already. Do you need me to scroll back? No. Okay, yes. Yes. Here, I'll rewrite them and make them fatter while you... That says, oh, that's kind of bad, me rewriting it. Like, polar, and we're just going to abbreviate nonpolar NP because we know that abbreviation now. Liquid. Okay, now can we scroll? See? Okay, so which of these would dissolve in water? So first of all, is water polar or non-polar? Polar. So carbon tetrachloride, polar or non-polar? Non-polar. It's balanced. Remember, so if it's all balanced, the charges cancel each other out usually, and it is non-polar, so that wouldn't work. Sodium chloride, does salt dissolve in water? Oh yes. Why? Because it's ionic and it's going to have that ion dipole bond. It's going to pull it apart. CH2, hydrocarbons, are they polar or non-polar? Non-polar, because everything's going to be real balanced here. The bond between carbon and hydrogen is a polar bond, so they're all going to cancel each other out. So that one is non-polar. Hydrochloric acid, HCl. It's very polar, isn't it? That chlorine is extremely electronegative. It's going to be stealing the electron pair from the hydrogen, making it positive on this side, negative on that side. So is it going to dissolve? Yes. Like dissolves like. We're looking for polar things. That's very polar. Ammonia, NH3. Polar, yes. Why?
Because that was one of the unsure pairs.
Yes, he got it. So here is ammonia, but just like Elisha said, it's got a fat, it looks like a little alien creature, doesn't it? Because of that big old unshared pair, that's going to be very attractive to the positive hydrogens in water, and it's going to dissolve. Easy, very, very AP thing to do that. They like you to evaluate because it shows higher order thinking skills. Okay. So solubility curves here, you read these in honors, so you should be familiar with them. But the main thing I want you to see is that as temperature increases for all of them except that one, solubility increases. Solids dissolve better in hot liquids than cold. So usually with the temperature, as temperature increases, how well it dissolves, its solubility increases. Easy stuff. This is honor stuff, right? Now, what can improve dissolving a solid and liquid? In our example, we can always think about a sweet iced tea. We're trying to get the sugar to dissolve. We put the sugar in and it's not dissolving. What do we do first? We try to stir it. So stirring can help dissolve. Okay, but it's not going to work because when are you supposed to add the sugar? Before the ice, while it's hot. So heat is the other thing that helps. Okay, and then the last thing is, so anybody got that Kool-Aid where it is not fake sugar, it's real, but you can put it in ice water and it'll dissolve. The little skinny packets of Kool-Aid, why can they dissolve when that packet of sugar can't? Yes. It's surface area. It's because they're so small. It's particle size. If you have a smaller particle, it can dissolve easier. Particle size. So there's my little particles. There's my stirring. There's my heat to help you remember it. Okay? Everybody remember that from honors? That was all from honors, right? Okay, so next, what about gas? Gas dissolves also into liquid. We know that from soda pop, from Coca-Cola. There's my little bottle of Coca-Cola there. So as temperature increases in a gas, what happens to solubility? Does it go up or down? It goes down. You heat up that Coca-Cola, it's going to go flat faster than an ice cold Coca-Cola, right? We know about that. We're from Georgia. Okay, what improves dissolving a gas in liquid? Well, we already said that cold temperature affects it. Now, of course, in science, cold doesn't really exist. Cold is just a lack of heat, but you know what I mean. Gas is going to dissolve better in cold liquid than in hot. Okay, and then what's the other thing? What do you hear when you open the Coca-Cola? Pressure, yes. So I always want to point out, so soda, beer, champagne, sparkling water, Perrier, they all have carbon dioxide gas dissolved in it. And I have a fish up here. What do fish breathe? Do they breathe the O in H2O? No, they breathe O2 just like us. So if your fish tank gets too hot, the oxygen will come out of the fish tank and your fish is going to die. So anybody killed their fish like that? Yes. So I killed frogs. So I've killed everything, all kinds of pets. But one time my boys had aquatic frogs. Have y'all seen those for sale at the science store? And I got tired of cleaning the bowl because they stink. So I decided, why not put them in a fish tank with one of those filters? That'd be much easier, just to take out the filter and put it back in. Well, that filter fish tank over-oxygenated the water. There was too much dissolved oxygen for the agitation. So really agitation is another one. That's how, as the water goes over the rocks and waterfalls, that's what puts that oxygen, the ocean waves, put the oxygen into the ocean for the fish. But so I had it too agitated, bubbles come out of the filter. It over-oxygenated the water and the frogs died, but they puffed up like the frogs in Shrek before they died. They got huge. They were so full of oxygen. I felt so bad. I killed Jumpy 1 and Jumpy 2 in one big accident caused by laziness.
To be fair, you did call them Jumpy 1 and Jumpy 2.
I didn't name him. My son Nathan did. The one who's the Georgia Tech professor now. Okay, not much imagination on the frog naming. Okay, Henry's Law. Yeah, but I killed them. I was tired of them. Oh, they stunk so bad. Okay, some pets are better than others. Solubility of gas and liquid is directly proportional to the pressure of the gas directly above the liquid. So that is Henry's Law from the other page. It's just more pressure. It's why we put Coca-Cola under pressure. So example is soda, like Coca-Cola. Scuba diving. So is anybody else in here scuba certified but me? Yes? Okay, then we know what we're talking about. So I took a class in college where I got to go scuba diving and get open water PADI certified. And when you go scuba diving, you breathe oxygen mixed with another gas in tanks on your back. And as you go under, it's pressurized, and then you're going down deep, and you're getting squished by the ocean is what I was diving in. I was diving down at Key Largo in the ocean. And so you get all this dissolved gas in your bloodstream. And if you go up too fast and you don't slowly change that pressure, your blood will actually fizz like soda pop and you'll die. Or you might get something called the bends, which is real bad. So no matter what, you could be being chased by a shark. As you're going up, you take out your breathing thing, it's called a regulator, and you blow out as you're swimming up. And you have to look at your bubbles, and you cannot swim up faster than your bubbles, even if you're being chased by a shark. You just hope he doesn't eat too much, and you know, maybe just takes a foot or something, and you go on up. I didn't see any bad sharks when I was there, but I did see a huge school of barracuda. What?
You have to be bleeding though, and they don't even go after human blood that much.
Exactly. So there was a huge school of barracuda. There was probably like 50 of them, and they were right over my dive partner. And there's a sign, danger. And so I'm pointing to the barracuda, and I'm going, danger. Well, there's a little thing called fire coral, and he's pointing to the fire coral that if you touch it, it burns. And he's like, yeah, danger, fire coral right there. And I'm like, no, there are 50 barracuda eyeing you. And so they used to say that barracuda don't really attack, but now they realize a lot of the things that were chalked up for shark attack were really barracuda attack. The barracuda attack lightning fast, and people will be attacked before they realize it. And the reason why they think barracuda are attacking so much is because at places people will feed them because it's cool to watch them eat, and then the barracuda are like, why are you not feeding me? I think I'll attack you because they'll eat you. Oh, you're not giving me food? People are supposed to feed me, just like you're a cat when they get mad because you haven't fed them. The barracuda get mad, so watch out. They're long and skinny and have a lot of teeth. Okay, section 11, spectroscopy, I can say it, and electromagnetic spectrum. So we already learned about the visible light spectrum, Roy G. Biv. What we're adding to it a little bit in AP above honors is knowing a little bit about the nanometers, the wavelengths. So we might have some questions about wavelengths, and we'll get to practice them with the I do, we do's. But the order of the rainbow, you know, is Roy G. Biv, and you also know that that visible light is just a tiny sliver of the entire electromagnetic spectrum. It's all light, it all travels at the speed of light, but that's the part we can see. So 550 corresponds, look up here, it is, that's hard to read. I think it responds, I didn't write it down. I think it responds to green, but we'll look at it. Let's see if I can y'all read it? What's at the bottom there? Or is it too blurry?
5 looks like it's about in the middle.
So, let's see if we got the colors on there.
Like where it's the brightest.
Right. We're going to go back to that. We'll look it up. I'm thinking 550 corresponds to green, but there'll be problems like that where you solve for a wavelength and then you tell what color it corresponds to. They like multi-step problems. So this is a multi-step problem. I think you'll be able to see them on the I do, we do's. Okay, so visible light is just a tiny part of the electromagnetic spectrum. And how you can remember the order of the electromagnetic spectrum is Ronald McDonald is very ugly, extra gross. I didn't make this up. This is like Roy G. Biv. So Ronald stands for radio, and that's AM, FM, and TV. McDonald stands for microwave, but that's not just ovens, it's also your cell phone is microwaves. Okay. Is infrared. Y'all know IR is infrared. We could just abbreviate that. Very is visible. Ugly is UV, and y'all know that means ultraviolet. Extra is X-ray, and gross is gamma rays. So UV causes tans and skin cancer. Infrared is heat. Visible, got eyeball there. Microwave, radio, and of course gamma rays turn Bruce Banner into the Hulk. But of course it's really high energy and will like give you cancer. Okay, good with this? Everybody knows Ronald McDonald's Very Ugly, Extra Gross? And I scroll. All right, so all of these are emitted or travel at the speed of light, and the symbol for the speed of light is a lowercase c. They're all emitted by the sun and other stars. They are all waves, and they differ in wavelength. And what's supposed to go here is lambda, but then I got all happy and I put lambda there too. And frequency, a frequency used to have a different symbol, and then they changed it to this one. And I'm not for this because that's the same symbol for speed. But you know, I'm not yet the queen of math and science. See my crown's over there? I'm running for it. I don't want to be the president because I want to be a benevolent dictator. So there, I want to just make my decisions because I know what would make it easier for kids to learn, and that is not the easiest symbol because it's the same way as speed. So
It also just looks like a U.
well, it's flat on one side, it curves around the other side. It's sort of like a V thing. Okay, so just know that red, whatever's on the red side, is got the bigger waves with the lower frequency and the larger wavelength. Blue, whatever on the blue side, is going to have higher frequency and smaller wavelength. Okay. Now, electrons also, you know, electrons are particles, but electrons are also waves. They have a dual nature. They have a very small wavelength, and the electron microscope works because of this. So the dual nature of light, the dual nature of electrons, they're similar. They're connected, photons and electrons. Okay, so Max Planck, I always think he has an interesting name. Max Planck, what a name. Planck's postulate is a theory stating that energy, like light, can only exist in discrete, quantized amounts rather in a continuous range. So we can't see it, but light is in little packets of light. It is not just a continuous amount of light coming for you. So just like how electrons have a dual nature of being like a wave and like a particle, guess what? Light has a dual nature of being in these discrete packets and in waves. It's a little hard to understand, but these things just have a dual nature. So photons are what these packets of energy, light energy, are called. In 1913, a Danish physicist, Niels Bohr, there's our Bohr model on the board over there, discovered electrons in an atom can only be in certain levels of energy. It is like a ladder. So like if you're climbing up a ladder, you can't put your foot in between rungs. You just fall back down. The only way to climb up the ladder is on the rungs. And so the same thing for the electrons. There is no ladder in between these rungs. They have to hop between levels. And y'all learned about that in honors. These have low energy at the bottom near the nucleus. It's higher energy in the orbitals and the energy levels further away from the nucleus. So they have to jump to go up. And what's that jump called? Starts with a Q. Yes, quantum leap. Quantum leap is the jump to go up. The amount of energy needed to go up a level is called a quantum. So here we've got particles and waves. UV and visible light both can make electrons jump up to an energy level, and that is called being excited. Okay? Infrared light, and this is an AP thing. This is AP only. Okay? So you have to remember that UV and visible can make them jump a level. Infrared can only cause them to vibrate. Infrared is lower energy, it'll just make them vibrate. They won't jump. Okay, and scrolling up. Microwaves cause them to rotate. And so microwave ovens are tuned to water molecules. So that makes the water molecules rotate, it causes friction, and it causes heat to heat up your food. Now you know how a microwave oven works. It causes your water molecules to spin and rotate. So electrons can be, and I've already said this can be described as both a wave and a particle. Okay. It's a particle. Light can be thought of as a particle also because light can spin a paddle wheel and electrons. How did I do this? Oh, I left off something, right? Nope. Okay, they can push. So and another thing is that shows that light is a particle. Someone's here. It is Devin. Welcome, welcome. So anyway, how you also know that light is like a particle is you can shine light on a certain kind of metallic surface and it can splash the electrons off. It's called the photoelectric effect. So if it was just pure energy, it would not have the substance for every action. There's an equal and opposite reaction to do that. So that these are sort of the experiments behind them being able to figure out that these things have a dual nature. Okay, so the lowest possible energy is called the ground state for electrons. So this is all review from honors. When they jump up to a higher level, they're said to be excited. I already said that. Okay. When they go back down, they can release the extra energy as light, and that's not just visible, that's the whole electromagnetic spectrum. So we'll say electromagnetic. In my honors class, we watched a video where they were showing how they discovered that, and they were able to show that the energy can also be UV. This is the first one they were able to show that it can be the whole electromagnetic spectrum. Each atom releases a different pattern of light called a bright line emission spectrum. And it's like a fingerprint because each atom is different. Y'all remember all this from honors? I know Miss Gordon's class did it too because I know they did the same labs we do with the light. Okay. Ready to move on to 312, properties of photons. We talked about electrons, let's talk more about photons. All electromagnetic radiation moves at the speed of light. Oops. I keep my sleeve out of the way. And that is 3 times 10 to the 8 meters per second. So this is something that I don't think is on your AP reference sheet. If it's not, you need to memorize it. You're expected to use it in problems. Somebody can look at the AP reference sheet and see if it's on there. It might be. Okay, so this is one of our formulas. C, the speed of light, equals the wavelength times the frequency. So V is the waves in cycles per second or hertz. That's the unit of frequency. It is symbolized Hg or S to the -1 power or 1 over S. Once again, something that makes things confusing that when I'm queen of math and science will straighten up. We don't need this. That's just, why do that? Let's pick one and stick to it, okay? Let's rule out some confusion. So wavelength is measured in meters. Wavelength and frequency are inversely proportional, meaning when one goes up, the other goes down. So here's an example problem. Can I scroll? We good with that? Okay. Okay, there's a relationship between, I left off my example problem here. An FM radio station broadcasts at a frequency of 96.9 megahertz. So that's million. Mega equals million. So in our Georgia lottery, Mega Millions is like billion millions. And they don't give away millions of millions. They don't give away that many. What is the wavelength? So mega is 10 to the 6 or a million. So what we do is we write our formula down, then we substitute in C is 3 times 10 to the 8th meters per second. What we're looking for, the frequency we know, it's 96,900,000. So 96,900,000. And then we're going to do S to the negative 1, so you can start learning that that's the same thing as hertz. And our unknown is wavelength, lambda. So to solve for it, we just do the opposite. It's being multiplied by 96,900,000 hertz. So we divide both sides by that, and we get the wavelength equals 3.09 meters. Put a box around it. So if we could see the wavelengths from this radio station going through the room, it'd be about 3 meters from peak to peak, or crest to crest, or trough to trough. So that's kind of neat to think about, isn't it? We can't see them, but if we could. So there's also a relationship between energy of light and frequency. And this is the formula. This is Planck, Max Planck. He thought of this, equals HV. Energy, this is, the E is the energy of a single photon in joules, and the symbol for joules is big J. So H, this should be lowercase h. Everybody kind of write over that. My Word thought it was very improper of me to be starting this with a lowercase, and it went back and auto-corrected it without me looking, didn't check it. But H is Planck's constant, which is 6.63 times 10 to the 34th joule seconds, negative 34th. Y'all should check and see if that's on your AP reference sheet also. If not, you're going to need to memorize it. Okay, so the frequency is in hertz. So here's the example. An AM radio station broadcasts at a frequency of 1340 kilohertz. Kilo means 1,000. Determine the energy per photon of its wavelength. So we put in Max Planck's constant, which is 6.63 times 10 to the negative 34 joule seconds, times that, and I'm going to just go ahead and write it as thousands. I'm going to add the 3 zeros. And that is in hertz. We're going to do second negative 1. So we just multiply, and it equals 8.88 times 10 to the negative 24th joules. Put a box around it. Those aren't hard problems, are they? Just fill it into the formula. Okay, y'all ready for the next one? I can see y'all are still writing. I'll move on the other side in case I block anybody. Okay, that's not a hard problem, is it? So I think a lot of the stuff we're doing in AP chemistry is not hard. It's just a lot of it. Like none of it's super hard, like real hard pre-calculus, but it's just a lot. Yes, ma'am? 6.63. Okay, ready to move on? Can I scroll? Okay, so here's another example. So sometimes we combine things we've learned. We've learned how to read these diagrams. That this, let me get on my right page here. Whoop. There it is. Okay, so we know this is 1s2, 2s2, 2p6, 3s2, 3p6, 4s2. So what element is that? Calcium. Yay, y'all are so smart. Proud of y'all. Calculate the wavelength in meters of, let me stop going too fast. Calculate the wavelength in meters of the electromagnetic radiation light needed to remove a valence electron. So which one of these are we removing here? The last ones, right? The 4s2. And this is our energy right there. the binding energy. So we know energy, we know Planck's constant, we can solve for frequency. Now, did they ask for frequency? No, but we're gonna have to get frequency before we can get wavelength. Do you see that? AP loves this. They love two-part questions where you have to solve one thing to get what you need for the other thing. So our energy, we're going to put this in 0.979 times 10 to the negative 18th. That's from right there. That is so just. They just rounded here, yes. So don't worry about that. Just know you'll be close enough to get the right answer. And now we fill in Planck's constant, 6.63 times 10 to the negative 34. And then what we're solving for is that. So we divide both sides and we get that this is negative 1.48 times 10 to the 15th. And we'll put our Hertz symbol there again. So I'm going to put a box around that because I might need to be able to see that quickly. And now I'm going to come down and do the next part of it, which is I have to put my speed of light, 3 times 10 to the 8th equals this, negative 1.48 times 10 to the 15th times what I'm looking for, lambda. So I divide both sides by that, and I get it equals to 203 nanometers. And they might ask us what part of the spectrum that is for the next part of our problem, and we would look, and that turns out it's UV. On the spectrum, that's in the UV lane. Okay, how are we feeling so far? We're on the last section now of Unit 3, which is 20% of the AP test. So you know this, you're going to know a big old chunk of it. If you do good on this one, you're in good shape. All right, last thing, the Beer-Lambert law. We're talking about beer? No, that's his name. Could you imagine your last name being Beer? That'd be kind of weird, wouldn't it? Now, my maiden name is Cash. So that was kind of weird, too, because it was a thing. People would always say, Lisa Cash, you got any? No. Or, Lisa Cash is trash. I heard it all.
Do you have anyone in your family named John?
Yes, I'm related to him. And so my fun facts on the door is I'm related to Johnny Cash. And I am so Southern, I'm related to him through the Cashes and the Cromers. Related 2 ways. So, anyway, spectrophotometry. So this is a type of chemical analysis that uses the intensity of light to determine concentration. So what you do is you take your stuff that you want to find out its concentration and you put it in a little test tube called a cuvette, okay? It's a little square test tube that's 1 centimeter on each side. And this is what the old spectrophotometers look like. And you put it in here, the light shines through it, and it tells you how concentrated it is. This is what the new ones look like. At East, when I came here, we had one that looked like this. But I came here during COVID, and I got hired right before COVID to teach forensics and zoology, I think. And then COVID hit, and they eliminated that position. And so then they hired me again to teach AP chemistry, honors chemistry, zoology. And so anyway, I came teaching chemistry, honors chemistry, and physical science. And this room had just been left during COVID. They walked away and didn't clean up because they thought they were coming back. They didn't know it was going to be months. Well, meanwhile, there was stuff in the back that was spilt and was reacting, and we put this haze in the air of some white solute, some powder that burned if it got on you. Like it would burn through rubber gloves. And so one of these was back in the chemical stock room, and when I turned it on, a big old puff of that white smoke came out of it, and it didn't work anymore. So it died because of COVID. It was one of the things that died because of COVID. So I threw it away. And Miss Raymond, who's the department head, was like, "What? That thing cost $1,400. You did not throw it away." And I'm like, "I did too, but if you want to get out of the trash, you can." She got out of the trash, she turned on, and she was like, "Oh," and she threw it away again. So we had one of those. And I was like, this is so sad. We're not going to be able to do those labs. But then as I was looking through everything, I found these. And these are the new ones. So we're going to be able to do a lab. We're going to do a lab hopefully with this if the new ones work. And I haven't tested them yet, but I will. But if not, we'll be doing a lab with this one. And this one, you use it like with your iPhone or with your phone, and it'll do a graph on there for you. So these are way better. That's what I used in AP Institute. So anyway, I threw away one of those. I threw away a lot of stuff. It was a mess. When I first came, I was like, oh, I am so glad I'm not going to have to clean up that mess. That is a mess somebody left. Of course I had to clean it up. It was awful. All right. So it shines light of a certain wavelength through the sample to a sensor to determine the concentration. So sometimes you have a mixture of things, and you'll look at a graph, and you have to figure out what you're looking for. So here we have an acid and a base. And if we were going to look for and it's a mixture. So you got a mixture in this little test tube of an acid and a base, and we want the concentration of the acid only. We don't care about the base. So we would set our machine to the highest point of the acid. Do you see how that's 320 right there? Okay. So that's our first thing, is you have to look at these humps and find the highest point so you know what to set it to. Now, sometimes these are smooth humps, but usually they're jaggedy. So when you look at the graph on the AP test, it might be a jaggedy hump, but you just find the tallest part of them, and that's going to be the answer. Easy question. Okay, so now there's a guy who figured this out, how to do this. Is Beer-Lambert, and this is the law. The absorbance equals the molar absorption coefficient, a constant, times the molar concentration times the optical path length. Well, in this, the constant, E, it's not really E, I guess it's epsilon, and C, the concentration, don't change. So A is proportional to the wavelength, to the concentration. The absorption is proportional to the concentration. Okay, so you get a graph. This is what you get. And you draw your best fit line through it. Now first, to get your graph, you want a 0 point. So first, the very first thing you do is you just put distilled water in your cuvette, and you get a 0 point. You need a 0, or else you won't have one on your graph. Okay, next, you make known concentrations and stick in there, and you get your points. Then you draw your best fit line through it, and then you put your unknown on, and it will give you a number, and then you can go over to see where that number hits the line and down, and you can read the concentration. That's not hard, is it? Okay, so use the graph to determine your concentration. For example, if your unknown 300 milliliter sample, so we're going to need this in liters, so I'm going to go ahead and put 0.3 liters. Had an absorbance of 0.4, what's its concentration? And then it says, what's its molarity? So we go over here to 0.3, we go over and down, and we can also look at it this way. Molarity equals moles per liter, okay? So our absorbance is 0.4, and we want the number of moles, and our amount is 0.3 liters, so we just multiply them, and N equals 0.12 moles. N stands for number, it's what you use for number of moles. Okay, last bit. So the AP test expects you to memorize. Oh, so first of all, this only works with colored solutions. If it's clear, that light's going to pass straight on through, of course. And they want you to have memorized some colors of ions. And y'all learned some of these when we did flame tests. Okay, so copper, so it's sort of similar. Copper is blue. Nickel, if you see a solution and it's green, I have a nickel solution in one of these little things around the room. You can see the color on it. If it is yellow or orange, it's usually got iron in it. This is not the firework color, this is the liquid color, the color of your thing that you're sticking in the machine. Cobalt makes a pink solution. So sometimes you're asked to analyze error. If you got a point that doesn't fit in your line and it's below the line, it's probably water contamination. So just memorize that. So, because there's a good chance that's going to be on the AP test. Yes, Mr. Elisha. I can't. I'm going to end the video. Science is great.